Hi class, welcome to the next section of chapter 4. This is chapter 4.5, the chain rule. So far we've kind of been going back and forth between talking about derivative formulas for functions and then derivative formulas for types of functions. When I say that, I'm talking about the product and quotient rules, where we're talking about a function that is made up of other functions. So for the product rule, it's when your function is made up of a product of functions. The quotient rule is when your function is made up of a quotient of functions. The chain rule is one of those types of rules. It applies to all functions. The chain rule is what happens, or is the method that we use to differentiate a function that is composed with another function. So when we have composition of functions, a function inside of another function, we use the chain rule. So up to this point, if we had a composition of functions, we would either have to expand it out if it was like a power of a polynomial, right? Like some polynomial to the 10th degree, we'd have to multiply that polynomial times itself 10 times. Now with the chain rule, we don't have to do that. Or maybe we had some complicated function under a square root sign, or anything to that effect, okay? So now what's going to happen is that the chain rule is going to allow us to differentiate many different types of functions. In all honesty, more difficult types of functions will be able to differentiate those now. Where beforehand we didn't have the tools necessarily available to do so. We're going to use the chain rule for the remainder of the course, which you'll probably hear me say that exact phrase several times throughout any course that I teach. But it's to be honest, it's one of the main tools that we have in our tool belt for differentiating. Okay, so I'm going to kind of give you guys two different approaches for using the chain rule. There's one that I use, which is really just to do it, and then there's a simpler method that I like to teach students when they're just beginning. Now, depending on how nested our functions are, right? So for instance, if we're taking a composition of functions, I can compose 10 functions with each other, right? So depending on how nested my functions are, really kind of increases the level of difficulty that we have. And so there's a way to kind of approach that, which it can still be confusing, but it's a lot simpler if you're not familiar with the chain rule method, okay? So before we start, let's go ahead and review all of the rules of differentiation. So I'm going to do this every so often as we go through this section. Chapter 4 is rather long compared to the other sections, except for chapter 1. Chapter 1 has 9 sections. Chapter 4 also has 9 sections, although the last section is all review for chapter 4. Okay, so periodically as we go through these sections, I like to go over a review of our rules of differentiation because there's a lot of rules. Okay, so for the first one is that if I have a constant times a function and I'm taking the derivative of that constant multiple of a function, I can pull out the constant and just differentiate the function and find the product. Okay, if I have two functions that are being added or subtracted together, and that is what my function is, and I want to take that derivative, I can separate it and take the derivative of each function separately and then add them or subtract them as needed. The derivative of a constant is 0. If you notice, I'm going back and forth between the prime and the Leibniz notation. It's just important that you guys are familiar with both notations because, again, like I said at the beginning of this section, sometimes the prime notation, it's easier to understand. Sometimes the Leibniz notation makes understanding the derivatives a lot easier, especially once we get into the higher levels of calculus. This Leibniz notation helps a lot. The derivative of just the function x is 1. So 4 and 1, 2 and 4 together is really how we differentiate polynomials along with 5, right? So if our function is a power function, variable to a power, we just bring that power down and then the power that we had reduces by 1. Okay, so we've seen this many times so far. The next one is that the derivative of e to the x is just e to the x. The derivative of any other exponential function is the natural log of that base times that standard function a to the x. Here, this was our product rule. If my function is a product of functions and I need to take its derivative, then I differentiate the first function, leave the second function alone, add to that, the first function being left alone times the derivative of the second function. Okay, then our next rule was the quotient rule. So again, if our function is a rational function, a quotient of functions, one function over the other, to take its derivative, the numerator is very, very similar to the product rule, except for with a subtraction sign in the middle, and then we square the denominator function. Then we start getting into our trig derivatives. So the derivative of cosine is negative sine. Remember C, right? I'm taking the derivative of a cosine function, so it changes sign. It always goes cosine sine, cosine sine, cosine sine. But depending on if it's a cosine or a sine, it determines whether or not we're going to change the sign, right? So C for change sign. The derivative of sine means the sign stays the same, so it goes to cosine, but the sign stays the same. Derivative of tangent was secant squared. The derivative of secant was secant times tangent of x. Remember, there's a secondary form you can have for this, but it's not really useful unless you're trying to be super crafty for some reason. At some point, maybe later on when you get into a higher level course. But for right now, secant and tangent is the preferred derivative of secant. Same thing for cosecant. The preferred derivative is negative cosecant times cotangent. And for cotangent, our derivative is negative cosecant squared. Okay, so that is all of our rules. So far, we have 15 rules. I think by the time we're done, we get up to, like, to be honest, not to scare you, but I think we get up to somewhere around 30. Okay, so the chain rule. So let's go ahead and get into it. So again, we use the chain rule and we have to differentiate a composition of functions. Okay, so if my function has the form f of g of x, so one function plugged into another function, then the derivative form for this, again, we're not going to go through the limit definition, I'll just give you the formula. You differentiate the outside function, but you keep the inside function inside of the function. And you multiply that times the derivative of the inside function. So again, just kind of look at this. When I'm differentiating this, it'll be two functions times each other. And the first function is the derivative of the outside function. Inside stays the same. Multiply that times the derivative of the inside function. So it's important to know which one is inside of the other when you're doing the chain rule, because you don't want to differentiate the wrong one. The outside function is always the easiest. The method that I like to show students at the beginning, or an easier way, is by using a U-substitution. However, if there's several levels, you might have to make a U, V, and W substitution, or even further than that. Okay, so the easiest way to show this is, like with other of our derivatives, is just to kind of do an example, right? So here I'll just kind of do a regular method. Here we have the square root of x squared minus 1. Up to this point, we didn't really have the tools available to differentiate something like this. Now, it's not a super difficult function to look at. We know how to graph this. It's the square root of a function shifted, right? We have a horizontal translation. But to find its derivative is difficult. Okay, so what we're going to do here is we are going to rewrite this as a power function, as a function plugged into a power function. So the easier way to look at this is x squared minus 1 to the 1/2 power. So it's very clear here, even here it's very easy to see that the outside function is square root and the inside function is x squared minus 1. So here it's even easier to see because we like to work with power functions instead of square root functions, right? It's just easier to differentiate. So here our outside function is this something to the 1/2 power. The inside function is x squared minus 1. So when I take my derivative, I will have my 1/2 move to the front as a multiplier. The 1/2 will decrease by 1, so it'll turn into a negative 1/2, and the x squared minus 1 stays the same. Okay, the inside part stays the same. The outside function gets differentiated. Okay, now I'll multiply this times the derivative of my inside function. The inside function is this x squared minus 1. So I will multiply this times 2x. Okay. Now it should be very clear here to see that you can simplify. Alright. As I said before, I like to keep this negative exponent. If you want to not keep the negative exponent, again, I don't care, that's fine. My preference is to keep it, so I will keep it here. But I will simplify this 2 and this 1/2, and I should get, I didn't simplify it, but we will simplify it as we come down, okay? So this is just a derivative form. If you wanted to, after you simplify it, you could write x over square root x squared minus 1. That's fine as well, okay? So we have the derivative. We know what it looks like, unsimplified. So what we're going to do is we're going to say, how would I have done this if I did use a substitution? Well, I know that my inside function is x squared minus 1, so let's call that u. Okay, so then I would rewrite this as u to the 1/2 power. So when I differentiate my new function with a different input, not the same input before, the input now is u, I will get 1/2 u to the negative 1/2, and then I have to multiply that times the derivative of u, because u is now a function of x, right? It is my variable, but I have to remember, I have to follow this formula. Differentiate the outside function, keep the inside function. Multiply that times the derivative of the outside function. And then I'll just replace those forms, right? That's the form that I have here. Okay, u, the derivative of u is 2x. My u is x squared minus 1. So my answer is 1/2 u to the negative 1/2, and then I have to multiply it times the derivative of that inside function. Okay. So when I make my substitution, this is what I get. And I guess I never simplified it, so that's my bad. But generally, you would simplify this all the way down. Okay. But it's nice to see here what the derivative looks like and how it follows this formula. Okay. So now let's differentiate e to the x squared. So before, when we were differentiating things like this, I had you use the rules of exponents in order to simplify this down to a form that was comfortable with us so that we could apply rule 7, right? We just used rules of exponents. We had constants everywhere. That wouldn't apply here. I can't use the rules of exponents to have a constant. So now that we have the chain rule, a lot of the more difficult exponential functions that we had are going to be a lot easier to differentiate. Let's go ahead and take a second and think about what function is the composed function. What function is inside of the other function? Once you identify that, go ahead and pause this video and take a second or two to try to differentiate this and see what you come up with, and then let's check our work back against what I have. Okay, so let's go ahead and try that now and give you guys a pause so that you can pause it and then come back. Okay, so hopefully you took a little time to try this out yourself and we're checking your work against this. So it should be pretty obvious here that for our composed function is x squared being plugged into e to the x. So when I make my substitution, my new function is e to the u. So when I differentiate e to the u, I get e to the u. But I can't forget that I have to multiply it times the derivative of that composed function. Okay, so the derivative is going to be e to the u times the derivative of u, where u is x squared. So now I can just plug all my stuff back in. I know that u is x squared, so this is e to the x squared, and the derivative of x squared is 2x. So then that is going to be my answer. Okay, so for our next problem here, we have something a little more difficult. We have x cubed plus 2x minus 1 to the 2/3 power times x squared minus 3 to the 4th. Now, we could take this and multiply it out. It'll be kind of a hassle, but at this point, we also know how to use Pascal's triangle, so it wouldn't be super difficult to do this last expansion. However, this 2/3 power can be a pain, right? So we'll square this term, but we'll have it under the cube root. So expanding these things is not going to be very fun, right? Especially if we have to differentiate after that and then simplify everything. So it'd be not a lot easier just to simplify as we go. So here we're going to use the chain rule, obviously, for both parts, but we also need to use the product rule, right? Because we have one function times another. So as we are using the product rule, we will be using the chain rule, okay? Because as I differentiate this first function, I have to use the chain rule. And as I differentiate the second function, I also have to use the chain rule, right? So to differentiate this, I'm going to have 2/3 times the polynomial that's inside, and then I'm going to subtract by 1, so I should have a negative 1/3. So 2/3 comes down, I keep this x cubed plus 2x minus 1, and I raise it to the negative 1/3 power, because I had to subtract by 1. So that's the derivative of the first function, first part of the first function, because now I have to multiply it times the derivative of the inside function. So I'll multiply this times 3x squared plus 2. Okay. And then I multiply that times my second function. So that's the derivative of the first function, but I have to also multiply it times my, what I would call g of x. Okay. I add to that now my first function being left alone, okay, and the derivative of my second function. So I will have 4x squared minus 3 to the third power, and then I differentiate the inside function, which is just 2x. Okay. So now, as you can see, the differentiation can get a little bit more tricky, and it will continue to do so as we go through this chapter. By the time we're done with chapter 4, however, we'll have all the rules and tools that we need in order to really differentiate any function. We're just kind of accumulating things in this chapter, right? So from here, we would not want to keep it in this form. If possible, we would want to simplify, which we can, because you can see I have one term and another term. Remember, a term is always separated by a plus or a subtraction sign. So a group of multiplications plus or minus another group of multiplications. So the things that I have in common are a constant. Okay, I have 2 and 4. Here I have a 2, so I have at least a 2 in common everywhere. Okay, honestly, I would pull out this 2/3 is what I would generally pull out. I pull out the fraction, so this will multiply. It will divide by 2, but also multiply by 3, so I won't have any fractions left over. I also have x cubed plus 2x minus 1 to some sort of a power everywhere, so when I pull that out from both sides, I'll pull out a negative 1/3. That will actually increase this by 1/3, which makes it just x cubed plus 2x minus 1. Both sides do not have 3x plus 2, so I don't have to worry about that. But both sides do have x squared minus 3. So I will look at the lowest power I have, which is this one, and I'll pull out the cubed term from both sides. Okay. So again, if I'm going to simplify everything, the common term that I would pull out is the fraction, which means that there's no fraction here at all for the first term. That will be inside of the parentheses. For the second term, this 4 times 2, which is 8, will be divided by 2, so it'll turn into 4, but it will also be multiplied by 3, so it'll turn into a 12. So there will be a 12x on this side. Okay. Pulling the x squared minus 3 means there will be no x squared minus 3 over here on this second term, and on my first term, I will only have one of them, 1x squared minus 3. Pulling out this x cubed plus 2x minus negative 1/3 means I will have none of that present on the first term inside the parentheses, and on the second term, only 1 will be there because it'll bump up by 1. So inside of my parentheses, coming from the first term, there's no 2/3 x, there is no x cubed plus 2x minus 1 of any kind, there is a single x squared minus 3, and there is a 3x squared plus 1. Okay. On the second term, this 4 times 2x bumps up to a 12x. There's no x squared minus 3 term, and this x cubed plus 2x minus 1 term turns into 1. So notice inside of my parentheses, I have no fractional exponents anywhere, which I did have. I also have no fractions. So inside of my parentheses now, everything is pretty nice. So what I'm going to do is I'm not going to keep it like this. I'm going to combine my like terms. I can multiply this out to a 4th degree polynomial. This will also turn into a 4th degree polynomial. So when I add these all together, when I multiply it out and combine, I have some single 4th degree polynomial. Hopefully I can factor that to have it in simplest form, and I can just have something times something times something times something. That's my goal. I always want my stuff factored. If you leave me this as an answer, I will be knocking points down, right? Yes, you differentiated correctly, and that's wonderful. But if you don't know how to simplify your answer, that's not okay, right? So depending on what your career goal is at this point, if you have to write some report and you have to find some sort of derivative, even if you're not differentiating it by hand, maybe you do it, through some other means. If you write in a report that this is the function that you're going to use, your boss is not going to be very happy. You have to just be in the habit of being able to reduce things, period. Okay. So this is my semi-simplified form. I'm going to multiply this out. So this stays the same. These first three terms, products here for this term on the outside, this GCF is not going to go away. I'm going to multiply this stuff out. So when I multiply out these two, I get out 3x to the fourth minus 7x squared minus 6. And then when I distribute this x, I get this fourth degree here. I can now combine terms, which is nice. And this is my polynomial. Okay, it's a much simplified form compared to what we see here. Okay, if this was your answer, look at how much of a mess this is. This is better, but compared to this, I mean, you know what I mean? Like, make it easier for me to look at. Okay, and then if you try to factor this out using the methods that I've shown in this course, this is not factorable, or any other method really, but this is not a factorable polynomial. But now I have it as a series of products, right? Something times something times something times something. So that's really how we would like to see our answers in this course. So let's go through another example. So here we have a function that's quite nested, right? I have some function inside of the square root, inside of another function inside of the square root. So I'm kind of 4 layers deep here, right? So when you're comfortable with using the chain rule, you can just go, right? Like when I'm trying to solve this problem, I'll just differentiate it. However, something like this, it is very useful to use the U-Substitution method. So I have 2x is inside of e to the x. E to the x is inside of a square root. The square root is inside of, it's x squared minus some square root inside of another function, right? So generally here, again, it's very important to understand which function is inside of which function. And I'll use U substitutions all the way through. So I can't go U and U and U and U. I got to choose different variables. So I'll use a U, a V substitution, a W substitution, I don't know, an M substitution, a lambda substitution, a delta substitution. I'll just choose variables that aren't commonly used, and I'll use those if I have multiple substitutions I need to make. So let's go ahead and do that, right? So for my first function, I have this function inside of the square root. So I'm going to start from the outside and work my way in, right? So inside of u, I have e to the 2x, right? So I can have x squared minus this other function, which is square root e to the 2x. There's different ways to break this down, right? So inside of this function, I have e to the 2x. Okay, so I can say w is e to the 2x, and then r is 2x. So I had to go u, v, w, and then I chose r because we don't use x, obviously. Y and z, we can choose, but we typically use y and z for other things, right, such as three-dimensional geometry. Okay, so I used u, v, w. I said, hey, let's go with r. I need the derivatives of each of these things because I'm using the chain rule at each level here. Okay, so the derivative of r is just going to be 2. The derivative of w, which is e to the r, is going to be e to the r times r prime, which if we make that substitution is 2e to the 2x. Okay, v is square root of w, so the derivative of v is 1/2 w to the negative 1/2 times w prime, okay, by the chain rule. So then we make that substitution for w, which is 2e to the 2x. So we'll have 1/2 times 2e to the 2x. Again, notice that the 2e to the 2x is all to the negative 1/2 power. You cannot simplify this 2 with the 1/2, so please don't get into that habit, okay? And then we'll multiply times w prime. So w is e to the r, or e to the 2x, okay? W prime is 2e to the 2x. So we have 1/2 times e to the 2x to the negative 1/2 times w prime, which is 2e to the 2x. U is x squared minus v. So when I differentiate u, I'll have 2x minus v prime. V prime, we have all of v prime here already. Okay, so 2x minus v prime, or 2x minus this whole thing. I'm not going to repeat it. Okay. I plug that whole thing into the square root, right? So my main function is square root of u, and taking that derivative is 1/2 u to the negative 1/2 times u prime. But we've already found u prime because we went incrementally to get there, right? So u is just x squared minus square root of e to the 2x. U prime is 2x minus 1/2 times e to the negative, or e to the power of 2x to the negative 1/2 times 2e to the 2x. So I just plug in my u, which is this thing, okay, and I multiply that times u prime, which I already found here, okay, in parentheses. There's not a whole lot to simplify because everything is being multiplied times each other, right? There's not like this plus this plus this. So the only thing that I can really combine together is this base of e to the 2x. So this 2 and this 1/2 can combine together to just be nothing. I'll have e to the 2x to the negative 1/2 power times the same base, which is e to the 2x. So I can start to simplify that. This first part, I haven't done anything. The 1/2 x squared minus root e to the 2x negative 1/2. It's the second part here that I'll be simplifying. So I'll still have this 2x. I can't combine that with anything. But here, this 2 and this 1/2 will simplify. Okay. And 2x to the 1/2 power is a negative 1 because these things end up just being multiples. So I get negative 1. Then I have e to the 2x times e to the 2x. So they'll add. So I end up with e to the negative 1x plus e to the 2x. Power-wise, it's negative x plus 2x, which is a positive x. So this is my simplified answer. Okay. So again, if you're having some problems with following this, which is completely okay, right? That's what the chain rule is all about, is being able to differentiate nested functions. I suggest you kind of just pause it right here before we go on to this next example, which is actually rather easy. And try this over again, right? Just rewrite this and try it again without looking at my answers. Maybe you use this u, v, w, and r. Maybe you go through it like you did for, or like we did, I should say, for C, where I didn't use any u's, v's, w's, and r's, and we just kind of did it, okay? So whichever one is more useful to you, try it on D, right? Try both methods, right? Try them 4 times over. It's really about practice. Math is all about practice. So as you're watching these videos, you really should be taking notes, kind of pausing it before I do these problems and doing these problems, especially when we have multiples. Like when I go over the first example, yeah, I don't expect you to be able to try this on the first example. But after we've done 1 or 2, if we have multiple examples, you should definitely pause this video and try it yourself. Maybe you saw the solution, which is great because it gives you an idea of what's happening. Go back, rewind it a little bit so you can't see the solution anymore, pause it, and just do it again and see if you can recreate it without looking at the solution. So I tell my students to do this when they're using this as lecture material without the video. So those of you who are not in my class, it's a really, really good method. Just keep doing the same problem repeatedly until you get the right answer, right? And then do it one more time to see if you can do it again, right? So the goal is to try to do this over and over without having to look at the solutions. If you have to look at the solutions, that's fine. Continue the problem. But that means that you have to redo the problem one more time. It's a really important, super solid piece of advice that I got from a previous professor of mine that I've used until this day. Whenever I'm having issues, I'll just do the same problem repeatedly. Okay. So to begin to move on to the next example, this is rather easy, but it's our first example of the chain rule with a trig function, so that's why I left that at the end. Okay. So same thing, I'm going to take the derivative of the outside function, which is sine. I know sine goes to cosine, and the sine stays the same, so it stays as a cosine function. My inside function is 2x, so this turns into cosine of 2x. And then I'll multiply that times the derivative of the inside function, which is 2x. So it turns into cosine 2x times 2. Okay, trig functions with the chain rule are actually pretty nice to do. So I move that to the front. We get 2 cosine times 2x. We'll do this again. Here I actually have 3 functions, right? I have a square function, I have a cosine function, and a 2 function. Sorry, 2 to the x function, 2 times x function. So I'm going to have 2 times cosine of 2x because my most outer function is the square function. I'm going to multiply that times the derivative of cosine of 2x, which we didn't just do, but it's very similar, right? So I'm going to have 2 cosine 2x because I'm squaring cosine of 2x. So that derivative, the outside function, is the square function. I'm going to multiply this times negative sine of 2x because remember, cosine goes to sine and it changes sign. So I get negative sine of 2x, and I will multiply that times 2. Okay, so the inside function is now 2x. The derivative of that is 2. We then simplify everything and we get negative 4 cosine 2x times sine of 2x. Okay, so we have one more example. Maybe do the same thing. Take a pause and try to differentiate this yourself. Now it's a little bit different because I don't have any actual numbers here, right? So I like to give these to my students every so often just to keep them on your toes, keep them on their toes. So it's important to understand what my variables are and what my constants are, right? T is my variable. Anywhere I see T is a variable, right? E is a constant, but it's a constant to a power, right? Sine is a function. A and B, are also constants. They're real values. So it's important to say, okay, well, what are my functions? E to the T is a function. Sine of T is my function. So when I differentiate this, I'm going to have to use, one, the product rule, okay? And not only am I going to have to use the product rule, but I have to use the chain rule in both places. So this would be like e to the 3t times sine to the 5t. But I can't use specific numbers because A and B are any number, but they are still numbers. They're just constants. So I don't treat them like variables. I treat them like fixed constants. Okay. So when I differentiate, I'm going to differentiate the first function. So that's going to be the derivative of AT. Okay. Or I guess my outside function is e to the x or e to the t, which is just e to the t. And then I multiply that times the derivative of the inside function, which is a times t, which will simplify to just a. Okay, so my derivative of the first function is going to be just a times e to the at. I leave my second function alone, and I add to that my first function being left alone, and I differentiate my second function. So here, just like we saw previously, my outside function is sine, so that will go to cosine. And the inside function is bt, which when I differentiate that goes to b. So I'll multiply this times cosine of bt times b. Okay. There is very little for me to simplify, but I do notice I have a common multiple of e to the at in both sides. So I'll pull that out as a constant. And then I'm left with the inside as a sine of bt plus b cosine bt. And that's it. I can't go any further than that. So that is our explanation for the chain rule. So as we progress through this course, when I have to use the chain rule, I'll try to go slow, one thing at a time like I do here. But after this section, I'm expecting you guys to know the chain rule, so we can breeze through this a little bit faster as we go through examples.